Hi, everybody. Good morning, good evening to all the folks joining us from all over the world. Welcome to this webinar on automotive semiconductor ecosystem. We have a couple of our beloved BE College alumni who are now kind of stalwarts in this industry, Dr. Aniruddha Mukhopadhyay and Mr. Subrato Roy. Uh, I wouldn't pretend to know anything about this ecosystem, but I do have worked on a couple of chips that go into this automotive systems. And I feel like this thing is like that fabled elephant. Like you just get to see aspects of it from different sides. You touch the leg, you think it is a tree. You touch the tail, you think it's a snake. So, like, quite glad that we are having this kind of a bird's eye view of this ecosystem. It's quite rare. Um, so, just to introduce our speakers, Aniruddha graduated from B College in 1984 from mechanical engineering, and he did his master's and doctorate from IIT Kanpur. And after that, he was with Tata Research and also did his postdoc from UIUC. He has been working in Fluent from 1999, which eventually got acquired by Ansys, and he has continued there and kind of in different leadership roles in US and globally. Today, he is a corporate fellow and lead chief technologist for digital engineering, focusing on multiple engineering domains like aerospace, automotive, electronics, and systems engineering. Subrato graduated in 2004 from ETC and is a technologist at TI's Analog Power Products Division. He has been involved in the development of power ICs for servers, personal electronics, automotive, industrial, and spanning textride, gallium nitride, BiCMOS, and other deep submicron processes. He is currently involved in technology development for future generation of power path protections. He has co-authored and authored 12 publications in TI's internal conferences and has 10 granted US patents and another 4 filed. He's a SMTS at TI right now. So without any further ado, let me hand over the stage to the speakers. Aniruddha, it's all yours. Please go ahead.
Thank you, Abhra, and thank you, IIEST community, for this opportunity. Uh, I'm going to just briefly introduce the topic of electronics in the domain of automotive industry, and then I will hand it off to Subrato for deep dive into um, ECUs and the overall role of electronics in automotive industry, test and validation efforts, safety and security, and all relevant topics. So in modern world, the cars are essentially computers on wheels. There are in excess of 100 ECUs in every car, ECUs being electronic control unit. And every aspect of car control that used to be mechanically driven or hydraulically driven are now driven mostly by mechatronic devices. At the center of that mechatronic device is an electronic control unit. You talk about Windows Wiper to actual motion control to HVAC to infotainment system. Everything is driven by an engine control system and electronic control systems behind the scene. So,
Aniruddha, if you
yes.
could just make it a full screen,
Oh,
then
yes, right. I just
yeah,
forgot about
thanks.
that. Thank you. So, so as you can see here, each of these functional component in the car, operational side, is essentially driven by an electronic control unit behind the scene. Now, there has been a journey in the automotive industry in the recent years for two different dimensions mainly, but there are more than two. There are actually other things, but electrification and automation, autonomous driving, these two are big initiatives in the automotive industry. Talking about electrification, it is geared towards net zero emission or reduction of carbon dioxide or greenhouse gas emission. And there has been a roadmap to really get to that net zero situation from IC engine community. And that roadmap is highly driven by the electrical background, but then it is managed by electronics. Today, we are going to focus mainly on the electronics element of it, but we have to recognize that it is driven by how the gasoline-driven cars are moving into electrical motor-driven car. And there is a roadmap for that. For example, in the very beginning, what was happening is it's called micro-hybrid, essentially taking auxiliary systems like start stops or basic level of hydraulic to electrical control systems. That's how this was um, introduction of various different electronic components into the car happened. After that, it began to do mild hybrid where combustion engine to regenerative electric torque assist technologies began to get introduced. And that would be limited propulsion systems, meaning if your one gas tank takes you to 400 kilometers, maybe 60 kilometers, maybe 100 kilometers out of that, 400 kilometers will be driven by electric motor through a high voltage battery systems. And high voltage here means from regular 12 volt to 48 volts. And then as the power of the hybrid technologies, the electric propulsion systems began to mature, we started to see that up to 50% savings, up to 50% of energy conversion began to happen through the electric motor. Then, of course, for efficiency reasons, for performance reasons, the voltages began to grow. Today, in plug-in hybrid cars, there are many commercially available cars that are really operating at 800 volt. Even then, there are more opportunities to really get to the point of net zero. And that's where the high capacity motor systems, high capacity battery systems are being looked into. And there are some commercially available cars looking into that domain right now. So that's in the form of electrification journey of maturity. And behind the scene, everything is driven by electronics. And we'll try to cover or introduce that topic in the next few slides. The other dimension is about autonomous driving. And in autonomous driving also, there is a series of maturity model or a roadmap that has been defined. Essentially, it starts with the driver is in control of the car. Some of the routine functions are getting automated. And every time automation is coming in, new sensors are introduced into the system. And ultimate objective is that humans are just riding the car. The autonomy has taken over full drive control. There are no cars available today that are truly level 5 ready in all sense of it. There are many nearing stage of this full automation, but realize the explosion of the sensor systems into the car. And anytime you're introducing a sensor, the interactions between all of them creates complexity. So what happened over the period of time is that this complexity has taken over the software system into the car, not just the electronic systems. The human interaction or the machinery interaction with that control system has become so complicated that despite initial aspirations, um, the car manufacturers, are seeing that they had an original plan. This chart, what going through a little bit more detail. What is happening is if you can see the name of the OEMs, they had an initial plan. They created a prediction, year of prediction. So in a certain year, they made a prediction. By a certain year, they will be able to attain a certain level of autonomy. But because of this multiple sensor explosion and because of the software complexity that came with it, they are beginning to sleep. To give you one example, Audi and Ford together started an AI company to meet this deadline that they had set for themselves. And that company's name was Argo Sync. It was in Pittsburgh area. Between 2019 and 2022, they hired in excess of 400 AI experts. And they were really going okay. All of a sudden, towards the end of 2022, they realized that the level of complexity has grown so bad that that approach to automation to reach level 4 was almost impossible. So eventually they actually dismantled that whole organization. And today they are predicting that this automation that was supposed to be very matured by next year is not going to come before year 32, 33, or even 35. And you can see that Nissan and even McKinsey had predicted that it will cross 2030. So everybody is now realizing that the complexity needs to be handled seriously. And that's another angle where electronics plays a major role along with software. And we'll cover that as well. Now, let's take a step back and really understand how electronics came into the car. So if you look into the good old days when we had Ambassador as the brand of car in India, or globally speaking, when we had car that had steering wheels that were directly manipulating through mechanical lever systems, the orientation or the direction of the wheels. From there, we went into a hydraulic system where the hand pressure was released, and now a little turn in the wheel would have taken care of the wheel-based directions much more smoothly and so on. So control became much easier. And then we moved from there into electronic systems. And this is the time when ECUs were introduced and electrical pulses were going through a motor with some pulse width modulation or some other type of control systems that actually manage the rotation of the tire on the road, and thereby the direction was, the driving direction was manipulated by the steering wheel. This has since gone into more detail, right? Because we have now cruise controls, adaptive cruise controls, and all kinds of complicated systems that actually made this more advanced. Behind the scene, the ECUs and the control systems have matured as well. And now if you go back to the first slide, I was showing that, you know, a car is actually a set of computers on wheels. Now you can imagine the total role of electronics into that ecosystem. And this is the time when I give the floor to Subrato to take us over into the electronic ecosystem. And Subrato, you can feel free to show your screen, or I can click for you.
I think, Aniruddha, it will be better if I control it myself so that I can time it out.
Sure.
So in the meanwhile, while I'm taking the control, can you go to the next slide? Yep. So, right, perfect. So I'll take over from whatever Aniruddha was showing. ECU. Okay. So guys, I don't want this to be a one-way conversation. So feel free to ask the questions. If it gets too long and we are about to breach our timeline, I will proctor that. I'll start with something which attaches your experiences to whatever we are telling it right now. So my first full-fledged experience with a car was when I got my first car. And if you have had that experience, you will see that any of the units, whether it's like the window roll up and roll down, or whether it's the wiper start, headlights, each of them you can call at as a separate unit which draws the power out of the battery. Now, the battery provides the power, the electrical current, in simple terms. But then for it to be relayed, for example, let's say if you have a recording camera or if you have a sound box, for the battery level voltage of 12 volt to get modulated, regulated to whatever that end equipment, in this case, let's say the headlights. Most of the cars have now gone into LED lights, or let's say the audio system to run. It may need a more specialized regulated system. And then those systems, whatever units, whatever power conversion units provide the power from the battery to the end equipment, those in simple terms are called as ECUs. So anything and everything in the car that you see as operating, you can assume as a single ECU. Okay. Now, it may seem like a very confusing general statement. So let's take it down to something which is more specific. Okay. So let me first take the example of a battery junction box. So if you open the bonnet of the car, unless and until it's an EV, a fully electric vehicle. If it's an internal combustion engine, you will see that um, usually on the right hand side towards the top, when you open the bonnet, you see a battery junction box. It's a black colored box which is sitting somewhere right on the top on the corner, and it has got multiple things where it is trying to interface with the internal combustion engine as well as with EV engines. EV cars, depending on the manufacturer, the battery junction box is still there, but the location may get changed. So um, if you just open the bonnet of your car and look at that battery junction box, the typical things that you will figure out, or you will see, are these block diagrams. I'll not go into the details of each one of them. The intention of this talk is to how do you connect what you see in your actual real life application to what you can, or what we have kind of been fortunate to get our hands on. And probably in the next few minutes I'll talk about the experiences that we had while designing a few of them. So uh, um, uh, the first thing that I want to talk about, if let's say it's an EV, electrical vehicle, you know that the battery packs can go to as high as 700 volt. And in that case, the safety element becomes very, very important. The chassis of the car, which is taken as a ground, it should always be isolated from the battery terminals. And in that respect, this is one very important IC, integrated circuit chip, that is used, which keeps on sensing what is the whether the isolation is maintained or not. So let's look at it in slightly more detail. What does that chip do? So basically, this chip, what does it do is that it has a series of FETs, and why there is a series of FETs, I'll come to it later on. But it you can assume that it's a single switch which connects S1 to S2 when it's on. So while connecting S1 to S2, what it does is that it closes the circuit on a resistor divider from high voltage HV plus terminal to ground through the resistor divider. And let's say if the insulation is not broken, then there is not going to be any current path. So guys, it all goes back to whatever we all have learned in our um, second year networks. So KCL, there is no current, there is no loop to be closed if the insulation here is not broken. I hope that my pointer is seen. If the insulation here is not broken, and you will always read 0, which is read by the microcontroller. Now, it's definitely possible that based on the insulation type material used, with time, humidity, some kind of accidents that has happened, this insulation might have got damaged, and you have got some leakage current. In that case, this resistor divider will start flowing some current, and you will read some voltage, and that voltage is read by the microcontroller to indicate that, hey, there is some kind of a leakage that's happening. It may turn hazardous for someone getting into a direct control, and the entire path has to be broken. So this pyrofuse that gets blown out, I'll not go into the details of it, but um, um, it's like a single fuse element which is electronically blown, and it is guaranteed that every time the electrical signal comes in, it will blow open every time. So no chance of failure. So we term it in terms of, or we quantify it in terms of um, failures, or in ppm, or parts per million, or parts per billion, ppb. We will come into those aspects of safety later on. How do we quantify, how do we test? But this is one aspect where the safety becomes uber critical. If there is a breakage in insulation, you do not want your battery pack to keep on supplying, and you would want your this fuse element to get blown away electronically. So there is a particular fuse electrical driver which does that. Um, the second thing is that when let's say you're drawing power of the battery pack is nothing but it's something which stores energy. So if you're drawing the energy or the current too fast, then it may get heated up and you may want to modulate that. So there are a lot of sensors, temperature sensors, humidity sensors, which are available. So this is a very simple block diagram on the bottom side that I'm showing, where from the battery, there is some external resistor divider, and then there is a temperature sensor. The voltage across the temperature sensor, which is inbuilt, goes inside, and that analog voltage is converted into digital for the microcontroller to read out. And if the temperature becomes too high, then you show this as a fault on your driver indication system. So this is one of the two chips that goes into the battery junction box. The second one is something which in the industry is known as the high side switches. So in the previous example, like I was saying, um, you want to get a breeze of fresh air, you want to roll your windows down, rain is coming, you want to roll your windows up, you turn on your headlights, or let's say you give your left or right indicator. Each of these ECUs or loads are supplied from the battery, coming in from a simple switch. Okay, so that simple switch is what we call as high side switches in the industrial parlance. And although I oversimplified it by saying it as a simple switch, that simple switch does a lot of activities. Most of the times, for example, let's say it's a car, it's an ADAS enabled car, and there is a front camera, or there is a radar unit which is trying to sense out. Those have heavy microcontrollers, and hence the output has large capacitors. So to make sure that whenever, let's say, your battery comes up or you start your engine, that does not take a lot of current, which we call as inrush current, you have some kind of protection built in. If, let's say, there is some fault, some accident has happened, some rain drops have percolated into the camera and it's caused a short into the front end ECU, you do not want that short to drain out the entire battery current or voltage. So it will disconnect as soon as it will sense the overcurrent or the short. So all these kind of protections are already built into this switch, which, as I said, is called high side switch. Yeah, Obro, please go ahead.
Yeah, hi Subrato. Just one, Subrato, hi. So one question. You were saying that if there is if the ground is maybe the insulation gets worse in the previous slide. My confusion is what is the microcontroller ground? I mean, the microcontroller will still see a valid supply at that case, or uh, because if this ground is broken, so what happens to the microcontroller ground also? I mean, is that
Right.
still intact or?
Right. Very, very good question, Abro. So before I answer Abro's question, so in one of the later slides, I'll talk about one of the components which I had the privilege to design with Abro. I remember those 2 years in which we came up with this particular part. And yeah, it is one of our best-selling parts. Coming back to your question, Abro. So all of the ECUs have their own ground, which is this particular ground symbol. And in spite of having that 700 volt battery, the chassis of the car is still considered as the ground. So the
Mhm.
ECU ground is still the chassis of the ground. And that is every system that, as far as I know, strives to isolate the battery ground or battery negative terminal to the chassis ground to avoid any harsh shock to human touching if there is an insulation breakage. So this ground, which on which the insulator, or sorry, the microcontroller is sitting, that is the chassis ground.
I see. Okay. And there is what happens if this ground to the microcontroller itself is faulted? I mean, is that a valid use case or that never happens?
Let me understand your question very clearly. So what you're saying is that what happens if, let's say, the connection to this ground versus the this ground connection to the chassis itself is broken. Is that correct?
Correct. Yes, yes. Basically, what if the microcontroller ground itself is questionable, or can that happen, or it's it's
Okay.
not a big deal
So
because it carries a less current, maybe. Maybe it carries a less current because it's not a that because your battery will carry a lot of current. but your microcontroller may not. So I think even if you have a fault, I would assume that microcontroller current would not produce a lot of voltage difference in the ground. So yeah, I understand. I mean, I understand what you're trying to point at. Yeah, I got it. I just thought a little bit. One more
Okay.
question is there a speed limitation here in the overall this thing? I mean, when you go to the microcontroller and come back and turn off all this, is there a spec on the speed that has to be,
Yes.
followed?
Yes.
Yeah.
So let me first completely answer the first point. So, Abhra, like we have seen and designed the TPS 2595 validation board and some of the EVMs, the ground is an entire plane. So it's not possible that in that PCB, the
Mm-hmm.
entire plane gets broken up. So a part of the question you have already answered that the current is already lower, and on top of it, the ground plane is strong enough. So even if let's say there is certain cracks with time, humidity, temperature contractions and relaxations, there may be some cracks and some resistance that will start developing between the microcontroller ground and the chassis connection, but that is still not sufficiently high to close it. Even if let's say it becomes an open completely at the end of the life, the microcontroller will not be able to close its voltage. So think of it in this way: the microcontroller is getting its voltage, but there is no ground path. So microcontroller
Right.
itself will show that it has a fault, and the car will not start at all.
Okay.
Okay. So now coming to the second question, and for the benefit of everyone, if you could repeat your second question once again.
So the question was, let's say, I mean, if the ground that you are showing insulation resistance of the chassis that is faulted, you would have an indication at VADC. It will go to the microcontroller and then it will come back and blow up your pyro fuse. So I am assuming there would be a speed, like it's a very pretty high speed requirement. The response time has to be very low. Is that current correct assumption? Because the currents will, or there is no speed limitation. I mean, what is the speed limitation in overall correction when a fault is detected? Basically, is
So,
there a
Abhra,
speed spec?
I actually do not know the exact answer of this particular question. From the construction of this device, I know that it's not very high speed. So the overall detection speed of the signal here is in the range of microseconds. Okay, let
Okay.
me revalidate my reference points. So when I say high speeds, I'm talking about nanoseconds. So the overall speeds in which this gets detected and the pyro gets blown up is in milliseconds. So milliseconds is still not large for a human to get fatal or some
Okay.
kind of a nasty shock. But we all know in our electronic parlance, milliseconds is as close as DC. So definitely, if there is a fault, most of the electronic equipments or the ICs here will get charged.
Got it. Yeah. Makes sense. Yes. Human use case standpoint, that I mean, a millisecond would be very less if you are concerned about human faults impacting a human interaction with the system. Yeah.
Right.
Thanks. Thank you, Subrata.
Okay, Abhra. Good question. So we have talked about these high side switches. I'll go to the last slide on this example of this battery junction box. And that is a reverse battery protection. And this is the context in which I wanted to probably take out an example of the work that I had done with Obro. So what happens is that I'm not sure how many of you have faced this particular problem of your car battery getting discharged. I have. Okay. And I had to call in a particular person from a garage who will come up with a battery with strong, huge cables, and they will connect that battery to the car battery. Now, we are all humans, we can make mistakes. What if while connecting the terminals of the battery that they have got it from the garage to the car battery, they invert the terminals? Okay. So this is what is called as a reverse battery condition. Okay. So what happens is that you are supposed to always get a plus 12 volt, which is a typical voltage of the battery that we put in our cars. But then if let's say this 12 volt becomes minus 12 volt, what happens in that situation? There are other situations as well. Let's say you are driving your car. Suddenly you had and you might have seen that as soon as you turn on the engine, and let's see, even if you do not run, your car is idle, especially let's say in Kolkata's hot summer, you'll see some kind of a sound, some humming sound, and that is not the sound of an AC predominantly, that's the sound of the alternator trying to charge the battery. So let's say in the condition in the event of an accident, that alternator was charging your battery and then your battery got disconnected. So suddenly what can happen is that your IC input can see very large negative voltage to the tune of, let's say, minus 100, minus 150 volt or something. So these are ISO Pulse 1 conditions, and I'm sure Abhra will be smiling because we all faced a lot of troubles in meeting those conditions to make sure that our chips keep on functioning reliably, they don't get damaged. Abhra designed one of the very critical components to make sure that even if, let's say, the input voltage goes to negative minus 20 volt, it does not get damaged.
Yeah, I remember this, Subrata. It was a pleasure working here. It was quite tough, but finally we did it.
Right.
Yeah.
So that is the job that this is what we call as ideal diode is that chip does and protects the ECU from these conditions. And Abhra, again, to give you something very interesting, there has been multiple Chinese competitors who have verbatim copied our parts. So this
Okay.
has been so commercially successful that they have even copied the grammatical errors in their data sheets, not only our overall specs.
Oh my
So
God.
yeah. So anyway, moving on to the next example. So this is of an ADAS sensor. So I myself right now own an XUV 700. As Aniruddha was showing, it's in ADAS level 2 in highways, in properly marked highways. I do take the pleasure of just letting the car drive itself based on the lane markings. It can speed up, it can stop itself, follow the lanes, and one of the critical components there is the overall SoC. This you can call it as a microcontroller, which takes the input from camera, the LIDAR, which is the low frequency, in very simple terms, radar signal feedback, and then it processes a signal to figure out what is the obstacle in front of it, and then it accelerates or deaccelerates the car. I'll not go into the details of it because, very frankly, I have never worked on this. This is a very, very complicated thing. And the reference that I was taking up previously of functional safety, or the ensure that it works every time. So think of it. You have put your car in cruise control. You're taking a sip of water. You want to make sure that your car maintains the lane marking. It does not deviate into the next lane where there is a heavy truck which is moving. So it again cannot fail. If it fails, it has to indicate to the user that it is failing. Please take the control immediately. So this talk also has that kind of a functional safety requirement. Um, on top of it is, if you go and search the recent IEEE papers, or in general, the research interests on the automotive microcontrollers, you'll see um, the safety aspect or the hacking aspect. So we all know about malicious viruses in our computers. And as Aniruddha has said, our cars are now becoming the computers on wheels. So what stops those computers on wheels to get hacked? So the safety protocols is also gaining traction, and all of these aspects, the ensuring that every time you want this chip to work, it definitely works. Also, how it is not prone to any kind of hacking. All those aspects are a different subject altogether, and we'll treat it probably in a next webinar. So from this point onwards, moving on. Um, this is another example. like I was saying, that you can have different loads that you are driving. One could be a very, very simple temperature sensor. And in the temperature sensor, what you need is accuracy. It is not drawing a lot of power. And when it's accuracy, you want the power supply to be as stable as possible. And hence, you want it to be driven out by a regulator, an LDO, linear dropout regulator. Sometimes when the power requirement is very high, let's say it's a microcontroller, it's a camera plus a lidar module, a radar module that it's driving, and the power requirement is very high, then you want to drive it with a DC-DC converters. So this is an block diagram, a very simple block diagram of a PMIC controller, and it has three DC-DC outputs to drive, one boost, and then one LDO. So um, uh, this with this example, I will go and touch on the next topic, which is the AEC. AEC is the large header under which all of these automotive safety protocols, like I was saying, that if there is a fault, you want that pyro fuse to be blown up. If there is an accident, you want that um, bib to get blown up and the airbags to deploy. Similarly, if let's say there is a microcontroller which is controlling your car to ensure that it's in its lane, you want that microcontroller to be working, not to be hacked by someone with a malicious intent. So all of this comes under this overall umbrella of AEC. And this is such a wide topic that we will take it up probably in a later stage. Or if, let's say, we have sufficient time today, we will try to see if we can get one or two subtopics underneath. At this point of time, let me open it up to wider questions. So feel free to ask your questions based on the slides that we have presented so far by Aniruddha as well as by me. We'll be happy to answer any of your questions.
So there is one question on the chat. Coming from a civil engineer, if all the cars become automated, do we need pavement markings or traffic signals on roads? Maybe Aniruddha, you want to take it up? Aniruddha, you are muted. Need to unmute.
Thank you. Thank you. Yeah, it sounds like a simple question, but it is attached to that roadmap conversation we were having earlier in terms of autonomy, right? The thing is, if all cars are automated, we expect that they know each other's coordinates and they can avoid collision or any other form of accidents. That's true. But that will need a lot of communication, a lot of calculations in real time, and maybe even faster than real time because it's a dynamic scenario and you want to play A versus B or various combination of situation and you find out the best route forward, right? To avoid that or to structure it more systematically, having the pavement marking gives a baseline automation paradigm. That means basically that most of the time the cars will be able to define the safe zone or the safe route. Now, there will still be lane crossovers, there will still be some marking missing, and that's where the perception algorithm or the sensor observation versus predictive control will manage that safety concern. Now, what Subrato was touching upon with respect to this question is a whole discipline of how safety is defined in automotive industry from an overall performance point of view, not for a particular electronic circuit. And those automotive safety integrity level, there is a whole discipline on how you create hierarchy of safety. The pavement marking falls into that category as well. And that's why the roadmap is so important. But Subrata, if you want to add anything, please go ahead.
Yeah. So I think if you search in the web, right, you will see the concept of connected cars. So in the connected cars, the very high level idea is that each of the cars in a particular geographical spot talks to each other, and that is the epitome of level 5 autonomous driving, where let's say you're sitting there in the car, you are the driver itself, is the passenger, and the car, let's say if they have to take an exit from the highway towards their destination, then it kind of talks with the car which is there on its left lane, says that I'm going to slow down, take a left turn. So you please accelerate, and the car behind me, please you decelerate and give me the space so that I can go and take the exit. So this is the highest epitome of level 5 autonomous driving, and maybe beyond. It is not there right now, not even in the Tesla cars. Uh, but if, let's say, that kind of implementation happens, and I'm absolutely sure it will happen in the future, then I completely agree to your question. We will not need any traffic signals. We will just need to have each car compliant to these protocols.
Thank you. Maybe we get access to the third dimension before these things start to happen. Another question on the line. Years back, I was told that tire pressure sensor is the easiest entry point to hack a vehicle. Is that the correct assessment? What are the guardrails to ensure security of a computer systems from security of computer systems from getting malicious actors from gaming control, turning the equipment into a 1.5 ton killing machine? If one of you, Subrata, can take it.
Go ahead,
Okay,
Subrata, if
so
you, yeah.
yeah. So so XUV 700. Not only that, Tata Harrier, Tata Safari, all of them have tire pressure sensors. So if you look at the actual sensor, so all of us being the hardware freaks that we have been mad enough to pull out these sensors, look at it ourselves, physically touching it, and it's a very dumb sensor. It is something which is a simple wireless, sends out the signal to the receiver there in the underneath the bonnet of the car. Now, if the hacking has to happen, as I was previously trying to describe, the hacking has to happen in the SoC, in the processor. And there are multiple ways in which this hacking can happen. It can happen while trying to interrupt the wireless signals, the interrupting or the pulsating of the wireless signals. That is not such a attractive or effective measure as of now. But then there is one of the newer hacking mechanisms that I've known is pulsating the power supply by disconnecting the battery. So do remember, in EVs, although the electric vehicles may have a battery of 700 volt to have the powertrain being driven, it also have 12-volt battery so that it can drive a lot of 12-volt rails as well. So if any of the processors is running out of that 12-volt rail, you can pulsate, or you can duty cycle the power supply to get into one of the test modes or master control modes of those processors. And then with that, you can change the feature of the controller or the processor itself. So again, if you search the web, there is lot of research that has already happened, work that has already happened, which makes sure that those kind of intrusions, the controller is protected against. So that's the part of my answer. Abhra, I see your hand raised, but I will let
Yeah.
Aniruddha complete the answer. Anything that he might want to add before you ask your question.
Just a quick note to add on to that is that cybersecurity overall has multiple dimensions, and one of them is what Subrata just described, which is hardware security, right? Hardware security and countermeasures. But then there are whole domain of the software cybersecurity that comes into the picture as well, and the software entry point and these trust levels, and how do you mitigate these risks in terms of encryption, non-encryption. All those things are evolving very fast. So yes, these issues are getting designed, the bus bars, the connectors, the signal processing, CAN, lean buses, etc., the wireless buses, they're all evolving at high speed in terms of more functionalities. But cybersecurity at the hardware level, at the software level, at the network level has taken a new dimensions. And particularly nowadays, it's not just the car, your cell phone technologies, your overall, anywhere you see electronics, The software hardware combination of cybersecurity has gone paramount. Every time a problem is fixed, there is no time to really rest. Immediately the hackers are acting and the next hacking is happening. And you probably are noticing what is happening all across the compute or the internet overall in terms of cybersecurity. Automotive industry is not sitting idle. There is so many different parallel activities going on. We can actually have a conversation around just on cybersecurity itself. One pointer I will leave with is that in North Carolina State University Computer Science Department, if you go to look for cybersecurity case studies, you will see how a completely shut down iPhone was hacked with experimental software and demonstrated how this hardware software combined cybersecurity can be protected. By the way, since iPhone 11 onwards, those problems are resolved. Automotive industry is learning this fast and furious. They're implementing these things at both levels, hardware and software.
Great.
I have one question. It's more from a system level or a market standpoint. We are pushing more and more, we are pushing more and more features into the car system, and it leads to increase in the cost, right? And what we saw is right after COVID, there has been a spike in, people coming up and buying newer and newer cars. But eventually, we saw the, share levels. Tata Motors first spiked up, and then it got saturated. So right now, we are going through a global recession, and more feature incurs a higher cost. So do we feel that the amount of features, the amount of technology we are incorporating, it might not exactly be commercialized to the level that we expect? Because the reason I'm asking this is, as we see 5G also, right? There was a hype with 5G and IoT, and we saw that it'll be used widely. But what I hear is 5G systems are also not heavily commercialized. I mean, we are not able to, churn as much money as we wanted or had projected. So do you feel the same way that we can see this day in automotive car also? I mean, with incorporating more and more
So let me
features
take the
in the
first
cost.
stab at the question, and then Aniruddha can complement on the previous question. So, Abhra, if you look at the 5G overall technology rollout, it was rolled out simultaneously in 3 or 4 cities in India, and then even in Bangalore. If you look at our experiences, it's not that we do not consume the high data rate. It is just that we are limited by the amount of time we are under the actual 5G promised data rate. So it's not limited by the consumption, it is limited by the supply. I
Mhm.
believe something similar happens in every paradigm of this overall electronic or electronic end equipments, be it servers, enterprise, telecom, or in automotive or an industrial. So if you take, for example, the industrial, or sorry, the let's first take the automotive. Uh, do compare the prices, average prices of cars. Let's say prior to 2020 and post, let's say 2022 or 2023, whether it's like MG, Mahindra, Tata, or let's say even Toyota, the overall price range of their high-end cars have significantly increased, and they are providing the overall value adds. So some of these car manufacturers like Mahindra and Tata, they do not have a very strong, deep, detailed R&D centers on these features like ADAS, and hence they take the third party, which we call as OEMs, like Mobile Eye, to integrate the ADAS system, and they
Okay.
definitely charge their customers to pay for it. For example, I now being habituated to the kind of convenience that I'm getting from my ADAS level 2, there is no way. I actually made this comment that when I was there in Kolkata and driving a manual car with no ADAS, it was being very difficult, and I did not want to drive. So it's all driven by, ultimately, we have had more debates on that, Abhru, on capitalism and consumerism. So as long as there is demand, there is going to be supply.
Okay. Yeah.
Aniruddha.
I think you answered it very well. It's just that there are some market dynamics that will keep changing the expectation versus the outcome, right? But overall, it is driven by consumer demand and it is driven by technology readiness. I think, Abhra, you covered that very well. Subrato, you covered that very well. Sorry about that.
Yeah. Thanks, Aniruddha. Very
Thank
good
you.
questions.
Thank you. But are you sure you could not drive in Calcutta because of your car or because of the people in Calcutta?
Yeah, let's not go into that topic, Abhra.
Okay.
So, Aniruddha, I had one question. I
Sure.
have worked a little bit on the communication aspects, wireline communication aspects within a car. So I see some sort on the low speed side, right? You have the LINs and the low speed communication protocols, right? And on the very high speed side, you have the proprietary protocols from TI and Maxim, and now you have the standards coming up.
Mhm.
Uh, I am kind of confused where Ethernet fits into all of this because I see all the companies still gung ho on the Ethernet standard, right? And even this new standards are kind of trying to map Ethernet into their funnels.
Very good question. It's all looking to that ultimate matured state. Like you would like it to be the first question about the pavement marking are needed or not. And then Subrata answered that if we are able to reach level 5, then really we don't need the pavement marking because V2X communications, vehicle to vehicle and vehicle to infrastructure, everything else, that communication, right? So you need that uniform access points, you need the cloud enablement so that a large bandwidth computing can happen in real time. And you need the ability to control from a cybersecurity point of view because as you know, Linux has lesser vulnerabilities and more control mechanisms built in from Department of Defense applications down to your consumer electronics and everything in between, right? So that's the overall journey people are looking for. The requirement for Ethernet, one thing is speed, no doubt about that. But the more ecosystem readiness for pseudo homogeneity or compatibility across the wider ecosystem players from EMS, emergency medical services, to emergency uh, police services, to any other things that are going to have newer interrupt on your car's operation. How do you take a car that is about to have a malfunction off the road, and how do you communicate with everybody else around that what is the safest way to take it off the road? All those things need to be thought through. And the current view, as I understand it, is that having a more compatible ecosystem with each other will give more agility, more speed, more safety. Subrata, please go ahead if you want to add anything.
No, I think you summarized it very, very well, Aniruddha.
So one experience that I had, Abhra, I mean, when I worked in FPD Link team in TI, there was a parallel Ethernet team also. And we
Yeah.
had this question, these two specs, I mean, the specs that we are meeting for FPD Link is almost similar what Ethernet is meeting. But even then, TI had their own proprietary protocol for automotive. FPD Link is catered to the automotive connections. What I understood was very from a very low level details, maybe with a limited experience, that there are two things. One is the speed, which Ethernet guarantees, but there is also a lot of focus on the length of the channel that one wants to attain with a certain loss for an automotive system. And those wires for FPD link, they were also very different from what we had in Ethernet in terms of the channel length and also the speed combined. So yeah, I mean that had been one difference that I could see, but I could see TI focusing on a separate protocol, not Ethernet, but FPD link they call it, just to cater to the automotive market for their mainstream communication from the processor to the cameras or the radars, basically.
Maybe I just want to add a quick comment on this particular topic. You are absolutely right, Abhra. But one of the other business oriented thinking here is that um, if you do everything by Ethernet, then it will be even harder to control your IP. You know, you can create all the patents you want. And as Subrata already said, breaking the patent from another country is no big deal these days, right? And You can get into litigation of all kinds. That doesn't solve the business problem, right? So in order to really protect your IP, you may always want to create a box within which your protected IPs and your protected protocol manages controlling that IP. And at the same time, you have buffers and you have protocols to connect to the rest of the ecosystem through Ethernet-like things. And
No,
that combination is going to survive.
but if you
Sorry, go
see
ahead.
now, right, TI had this FPD and Maxim had the GMSL, right? Now, there are two competing standardized protocols that have come up. One is ASA, which seems like getting more traction, and even TI is a signatory to that new standard right now. So, like, I mean, the other argument against proprietary protocols is that, like, definitely a GM or a Ford would like a open protocol, right? So they can mix and match components from different vendors. But my initial question was not that. So Ethernet. I mean, right now, what I understand, they do both low speed and medium speed communication over the Ethernet. Like, let's say, radar data is processed at the edge, and then information is being passed, not raw data, to the main controller.
Correct, correct.
And then you have LIN for controlling LEDs and switches and whatnot.
Mm.
So, and even these protocols like FPD can funnel I2C traffic or GPIO traffic over FPD.
Mm.
So you have the high speed bus, you have the low speed bus. Why do you need a medium speed bus? That was more of the question.
Okay, okay. I mean, my observation is that the jury is out. It's not that it is set in stone. And because the roadmap got stalled, the L3 to L4 transition on autonomy is really not moving at the projected speed like before. And now people are trying out different transitional paths. And it is not just on this communication protocol. That's just one element of it. Even the electronic control architecture itself is going through multiple evolutionary pathways, right? So zonal control, domain control, central control, those things are still worked on. If you look into the Renaissance approach of how the whole infrastructure should look like in future, they are trying to build ecosystems. If you look into SOFI, COVESA, all these consortium-based approaches, they are trying to parallelly address these multiple moving pieces together. So you are right that eventually it may be so that for inter-car communication or I2C or V2X, all those individual communication paradigms, they may define exactly what is the priority of the network that they're going to use or protocol that they're going to use. And right now, I don't think there is a solid consensus yet.
Right. And on top of that, Abhra, you also consider the legacy part of it. A lot
That
of
is
things are
true.
changing in the automotive ecosystem, but you definitely don't want to change all of that together and take the risk and the cost. So a lot of it comes from the legacy also.
Absolutely. And the other more important thing, which is ground reality, even if the new cars reach the level 4 autonomy and level 5 autonomy and so on and so forth, there will be still millions of cars in the overall road system that are from the legacy technologies. And communicating with them will not be using the most modern paradigm. So how do you manage that? So this transition will take sufficiently long time. And we will deal with this heterogeneity over that period of time.
Okay, thank you. So I think we are almost out of time. I don't see any additional questions on the line. Okay. Thank you both Aniruddha and Subrata for this delightful
Thank you.
introduction. I guess we'll have more of these. We'll follow up on different domains. Looking forward to those. Thank you again, and thanks everybody for calling in. Have a nice day.